So we currently use CDCV, centralized controlled demand ventilation, to manage air changes on campus. We have it installed in 13 buildings with several in construction. All but one are retrofit projects. So let's just take a look at how CDCV works. I know there's a few people out here that probably knows how it works pretty well, but can I get a rough show of hands of people who are familiar with this type of system? Oh, okay, pretty much about 50%. Yeah, so basically the system begins with room sensors which measure air quality at various locations throughout the building. And then an air router pulls air samples to the sensor suite, which analyzes the air samples for TVOCs, CO2, particulates, and other indoor air quality measures. An information management server tells the VAV controller to increase or decrease air depending on what the sensor senses. And then all this data is recorded and logged for analysis. And this slide is just going to demonstrate a little bit how the CDCV system architecture works. So a vacuum pump, oh, it doesn't seem to be working. Yeah, so a vacuum pump pulls a sample of air from both the supply and the exhaust air ducts. And the reason why it's pulling from both the supply and air is because the differential between the supply and the exhaust is what the sensor analyzes and monitors in order to tell the HVAC system to increase or decrease the airflow. These are just some examples of some of the CDCV components. Sometimes we'll bring samples of them to pass around, but we just wanted to show you some pictures of what goes into our buildings. And this is a list of what the sensors detect and sense for. You can see that we use 2 TVOC sensors. That's because the PID senses a range of VOCs a little bit better than the metal oxide and vice versa. So by using both of them, we feel we're getting a good variety and range of VOC sensing. And the other thing I want to point out is that we also have a lot of added safety and energy saving features that aren't connected at all with the CDCV. Things like red buttons, lab display units, and occupancy sensors. And these are some things I'll talk about a little bit more in a second. But what this shows is that the Smart Labs system is not a all or nothing proposition. It's kind of a a la carte, add as you go type of situation. So whatever we're presenting to you right now, you don't have to accept it completely as one package. You can mix and match and just kind of use it to however your institution finds it most useful. So the red button is a override button that's not connected with the CDCV system, and we tell our lab occupants to push the red button in case of an emergency or if there's some sort of spill that were to occur in the lab. And what that does is it increases the airflow into the lab to its maximum in order to help clear the space and ventilate the space as much as it can if that sort of situation were to happen. The other thing that we have is what we call a lab display unit. And the lab display unit provides real-time feedback to lab occupants so that they are aware of room pressurization and air change rates. As Alan mentioned, and also Phil, providing feedback to our lab occupants is a really important concept, because we feel, if they know what's going on in the lab, that it really they're really kind of like partners with us in terms of our energy savings and safety goals. And so things like lab display units and what I'm about to talk about in a second is really important for making sure the Smart Labs program works. So all these added safety features we kind of look at as sort of a safety net for the whole system. Things like this FAQ handout that gives you information about the labs, which we have for each one of our smart labs, town hall meetings like Matt mentioned, and also a web-based CDCV building information system, which provides feedback to the lab occupants on everything from how open their fume hoods are, or how often their fume hoods are, and how at what level they're even at, what the air change rates are, what the contaminant levels are for the different sensors, and that sort of thing. And so again, it's because we feel the more that the occupants know about what's going on in the lab, the more it can be safe and help us achieve our energy saving goals. So just to summarize what we're doing, as Mark and Matt have already mentioned, but just to drive the point home, what we're doing is we're reducing the air change rates from 6 to 4 in most labs and 2 when the labs are unoccupied. The CDCV senses chemicals and increases the air change rate if it senses an increased level of the contaminants. The sensors fail safe to 6+ if something were to go wrong with them, and we replace them every 6 months. So hopefully it's not too long before we find out if there is a problem with the sensors, which usually there isn't anyway. And we have other safety features such as the red button and also visual displays to enable the lab occupants to know what's going on in their labs. But I also want to take a second to address some of the shortcomings of the CDCV system and the Smart Labs program from an EH&S perspective, because we recognize that there are a lot of EH&S professionals out there that aren't necessarily fully on board with some of the things that UCI is doing. So I think it's good to actually acknowledge what some of these shortcomings are. You know, just because a CDCV system is not a simple, you install it and everything in your lab environment is safe and everything is perfect, and you just provides a turnkey solution that you never have to worry about anything else. There are a lot of drawbacks, I guess. I mean, the sensor suite is not going to capture everything. The sensors are located very far away from the breathing zone of the occupants. So as EH&S professionals know, that's not necessarily giving you a representative idea of what lab occupants might be being exposed to. And also there is a time delay in increasing the air when air is required. Other challenges that EH&S professionals face is the change in research operations, changes in inventories, and there's always a never-ending variety of operations and chemicals to reassess. That benchtop assessment that Mark was referring to, obviously it takes a lot of manpower to do those assessments, and the reassessments have to occur when there are changes in the lab. But even if CDCV is not perfect and does not solve all your lab air problems, it can be a helpful tool for EH&S. And the Smart Labs program, if it does anything, it helps emphasize the vital role that EH&S continues to play to monitor changes in the lab environment, to perform ongoing risk assessment, to perform exposure monitoring, implement work practice improvements when necessary, investigate potential complaints, and provide training. So to date, this is the results of our benchtop assessments. So we're finding that about 80% of our lab rooms can have air change reductions. So we feel like, you know, once you go out there and you start assessing things, that you will find that there are a lot of labs that there aren't a lot of harmful activities taking place on the benchtop, or you'll identify areas where you can implement good industrial hygiene practices and move the practices to a fume hood or another local exhaust ventilated enclosure. So just in conclusion, we strongly believe that safety is not being compromised by our energy savings. Lab air change reductions need to be determined by a little bit of flexibility, and that's always a evolving and changing process. Containing contaminants at the source, actively involving EH&S to be a part of continuing risk assessment, and reassessing the labs when any changes do occur. I guess, and the other thing I guess I just wanted to add to some of this is that I guess instead of being inflexible or dogmatic in our approach to environmental health and safety, we really should look at this as an opportunity for EH&S professionals to find a lot of value within your institution, and even more exciting and new ways to function within your organization. So, as Mark mentioned, we have an investigative protocol where we're trying to, I guess you could call it, quality control our risk assessment. We're just trying to verify that our risk assessment is actually working. And we're kind of on the initial stages of it, and we know there's a lot of room for improvement. And so I welcome everyone to take a look at the document that's in your packet, and email us and tell us how we could do it better. But for right now, what we're doing is we're evaluating and optimizing the laboratory for airflow and air mixing, and we're using a helium bubble simulation machine, which I'll just show you in a second. And also, we're making sure that there aren't any overexposures to chemicals in the lab, both at 4 and 6 air changes. So this is a video. I don't know how to get the video part to work. Well, it's not that important. Okay, but anyway, basically, so the helium bubble simulation machine, what you would have just seen is how the bubbles move about through the air. And basically, they're 2 millimeter helium bubbles, which allow us to see where there's dead spots in a room, how the air is circulating, and we can qualitatively at least compare it to 4 and 6 air change areas. And at least right now, we're not seeing a great deal of difference. And again, this is just qualitative observation, but it is some observation that we're able to utilize to see if there's good air mixing taking place in a room. And also, we're maintaining a database of exposure monitoring that in all of our labs. I mean, that's initiated by many different reasons, either the benchtop assessments, indoor air quality complaints, if we have a special directives from Cal OSHA or programs where we're trying to monitor for carcinogens and that sort of thing. And so we're keeping a big database of all of the areas, some of them 4 air change area rooms, some of them 6 air change area rooms. And since the Smart Labs program has been in existence since 2008, we haven't been getting any overexposures, which I would assume most people would say is the case in a lot of your labs, because obviously if you're having an overexposure to a certain chemical, that's a very bad thing, and putting a little bit more general exhaust dilution ventilation isn't going to be solving your problem. You're going to have to do a lot more than that. This is just a simplified example of one of the substances that we monitor for. Methylene chloride is just a common chemical. I'm sure you've seen it in your labs as well. And again, typical result were we monitored for a short-term exposure level sample, 15 minutes, and we got less than 3 parts per million, where the Cal OSHA standard that we abide by is 125. And this is just one simple example, but most of our monitoring results are. This is a changing process right now, and these are other ideas that we have for improving the investigative protocol. And like I said, if you take a look at what you have in your packet, and we're open to ideas on how we can verify our risk assessment a little bit better. So now I want to turn our attention to ANSI Z9.5 standard, which was recently updated in 2012. Everyone should really be familiar with this, whether you're an EH&S professional or not, just because it mentions a lot of good things about safety that also relate to energy efficiency. We're going to look at 2 parts that UCI is in the process of implementing. So one is the laboratory ventilation management plan. This is a part of the document that provides a lot of requirements and specifications for the issues that you see listed here, and it also addresses a lot of changes to your HVAC system that will affect lab occupants. And implementing it at UCI is a team effort consisting of EH&S, facilities, design and construction, and the lab occupants. Another part of ANSI Z9.5 that we're in the process of implementing is reducing the minimum exhaust airflow through our fume hoods when the sash is closed. As part of this effort, we performed a study to determine how much we can safely reduce the flow of fume hoods in our labs. I think it was Alan that was talking earlier about how it's a good practice to close the sashes, and yes, that is good practice and that does save energy, but when those sashes are closed, ANSI Z9.5 says you could reduce the flow in the hoods even more than what is currently acceptable at 25 CFM per square feet of work surface. So without getting too much into the details of what the standard says, that was the point of the study, to see how much we could reduce the fume hoods below the current design minimum of 25 CFM per square foot of work surface. That's probably what all your fume hoods are set at as well, because that's not just a California thing. Some of the safety considerations that the standard mentions and that we also took into consideration were things like what processes were being done in the hood, hood containment ability, potential for additional corrosion in the exhaust duct because of the reduced airflow, and the effect on exhaust discharge velocities. And so these are just results from the study, and for a 5-foot hood, you can see we could make reductions of about 33%. Same thing for 6-foot hood. And making these reductions based on $5 per CFM per year cost for a 5-foot hood. These are some of the savings that we hope to realize from our fume hood driven labs. So those are just some of the ANSI Z9.5 issues that we're focusing on, but it's a good document that everyone should be familiar with. And now I'm going to turn the talk over to Fred, who's going to talk about exhaust discharge.